kinda like complicated. I never know what I'm chasing, no. I don't need someone to save me, but you appear like a lightning bolt. Maybe you're a wizard, 'cause you're busy. There's magic in your rhythm, like a shockwave to my system. Maybe you're a wizard, 'cause you're busy. 'Cause every time I'm with you, you're my one and only elixir. Like a magnetic attraction, a supernatural vertigo. It's a chemical reaction, something I never imagined, no. Maybe you're a wizard, 'cause you're busy. There's magic in your rhythm, like a shockwave to my system. Maybe you're a wizard, 'cause you're busy. 'Cause every time I'm with you, you're my one and only elixir. You're
Wait.
I'm here. I'm here. Didn't mean to scare you there. Happy Thursday.
Yeah, happy Thursday. Oh, my
EDIO
light's not on. Just a second. I need the ring light. I just my lighting just isn't flattering without it, you know. I've got to
use the Elgato ring light or something else.
Yeah.
Oh yeah, there you go. Yeah, it's nice. It's a
I
beauty.
love it. Yeah, I can change the color temperature and the brightness and
yeah, it's a great light.
And turn it on with my phone. It's fancy. It's a fancy one. It
Well,
was your
welcome,
suggestion. I got that because of you, Edmar.
Did you? Oh, that's right. Yeah, that's right. Yeah, no, they're great. I mean, so obviously there are lots of different ring lights and stuff, but I feel like, you might as well start with the best one and never go back.
Yeah, when I first started, I was terrible.
What were you using?
Backlit. I don't know.
We should go back. We should go back and
take me under his wing and has taught me some of the ways.
Well, it's great to see everybody here. I see some people in the chat already. So awesome to continue this project. Well, this week was pretty big for a couple of reasons. Number one, CES happened. A lot of really fantastic announcements across the board from NVIDIA, from gaming to robotics. Obviously, we announced new series of GPU. So very cool stuff. I'll post a link to a blog where kind of all the announcements are very clearly one after the other, so everyone can catch up quickly. The other thing that happened this week, though, is that the sessions were posted to the GTC website. So GTC is coming up in less than 2 months now. We're about 2 months from now, March 18th to 21st. It's in person and virtual, but we're hoping that anyone who can come will come, because Eric and I will be there along with many people from the NVIDIA team. We would absolutely love it to see you there and meet with you. We want to also connect you with different developers on our team who can help you with your projects. I was just chatting with someone earlier today on the Discord server who recently joined Inception. For anyone out there working on a startup and you want to learn about NVIDIA's great startup program, the Inception folks will also be at GTC. It's a great program. Anyway, so check out nvidia.com/GTC. We'll post a link in the chat which gives you a little discount code for attending. And then let us know if you are planning on attending so we can set up meetings beforehand. It's going to be really fantastic.
I've got a question.
Are you like, you're set?
Yeah. So this stuff we're working on, the F1Tenth self-driving car, we're making it into it's going to be a session.
Oh, that's awesome. Really? So tell me about that.
So
go back to the slide.
Well, the goal, the deadline is turned from a goal to a deadline, is to get this car driving itself by GTC and turn that into a DLI lab, so that not only will we have the hands-on session at GTC, but I'm not sure how long, but we should have a DLI course for anyone who wants to do this. And
that's awesome. So the DLI course at GTC, so typically in those courses, people have like their laptops that's set up there for them, right?
Well, we'll be doing it with virtual machines.
Okay, great. So
I don't think you even have to be on site to do it. I don't know for sure. It's still kind of like, we are trying to have the virtual machines these, and we had them last GTC, and so I think we'll probably have a mix. Yeah.
How amazing would that be if someone who's been following along on your live stream series actually attends GTC and is there? They'll be the head of the class.
No. I want to have you guys there.
That'd be great. Oh, that's awesome news.
How cool would it be if someone from the evangelists, or if someone from the live stream like did it before, kind of got it working themselves before GTC and joined us?
Man, you know what? I don't know. I know you probably thought about this, but
are we allowed to do that?
It would be awesome to actually show off the real car actually there too. Maybe set up a little racetrack.
I'm working on it. I'm trying. I definitely want to. I don't know if I can meet that deadline.
Yeah, that's pretty crazy. But that would be awesome. That's a nice stretch goal.
That is my stretch goal, and I'm trying for it, but
that's awesome.
Can't promise that one.
Well, if anyone's working on any cool winter themed art, we would love to submit it on social media and use the hashtag Winter Art Challenge. I can't tell you how much everyone in the community, your work inspires the team at NVIDIA. We always celebrate and share this stuff internally whenever we see someone post something. So it doesn't have to be a super fancy artwork. It could be anything that has some kind of winter theme, including in robotics. We've had, I think, Matthew Schwartz did a really cool thing with a puppet. Not necessarily robotics, but it was pretty neat. Where he attached, what was he using? He was using a controller actually to in real time control a puppet. Anyway, so we'll look forward to your submissions there. We had this live stream a few weeks ago with the team from Foundry, and we talked about updates to Nuke. So if you use Nuke for compositing, they've added additional OpenUSD support. So really cool. And we see this across the board with many DCCs now, that they're really leveraging the power of OpenUSD. Obviously, with Apple's and other people jumping on board to Alliance for OpenUSD, we're seeing a great adoption across the board. Really exciting stuff. Let us know if your company's leveraging OpenUSD. We'd love to chat. And along the OpenUSD subject, we have Aaron Luck's great series on YouTube. We'll post a playlist on the link. But this is a great, really, really digestible bites, like 5-minute videos. You can really dive into and learn about why people are leveraging OpenUSD and get some hands-on experience with Aaron's guidance. And then I know Eric has been a big fan of, obviously, Isaac. He's leveraged Isaac a lot in his work and in these live streams. The Isaac team does have their office hours kicking off again in 2024, starting next week. I believe Isaac Sim kicks it off next week, and then the following week will be the Ross team. So it's a great place, just like this live stream, to come and ask your questions with the developers, chat with other users in the chat. It's also, and speaking of that, we've seen a lot of people in the community kind of meet each other in these chats. So feel free to introduce yourself, talk about your project. If you need some help, you might find a good collaborator there in the community and the chat.
I think I might start to. I don't know if we heard back. I think I might start to help out in those office hours.
Yeah, let me. And actually, that's a good point. Let me. It's a good reminder. Let me ping them and see. It'd be great. I think your presence would be fantastic.
It depends. We're not sure.
Very cool. So look, we got Papa Chuck in the chat. So are we hitting the steering today? Is that what's next up or not yet?
I've got a deadline now, so you're going to see
get serious.
getting done during the week, just not during the live stream. So I think I'll start off by catching everyone up to what I've done over the week and sharing a few lessons that I learned.
Sounds great.
But basically the core lesson I learned, and one thing I was looking into, let's see, I need to pull up Onshape and share my screen. Just a second. Let's log in here. All right. Here it is. As it currently stands, this is a complete template. And you know what I learned is that, okay. If you're doing a simulation in Omniverse of a robot, and if you are controlling your joints, your throttle, and your steering directly, then spherical joints are fine. And you could just model those spherical joints in OpenUSD. But if you want to do something like reinforcement learning, which we all think is so cool, and we definitely, I'm headed as fast as I can in that direction, right? Because it's so cool.
Exciting.
And if you're not familiar with reinforcement learning, let me just quickly explain that reinforcement learning is where you would put, say, a robot into some kind of a physics modeled environment, and then you actually teach it with a reward system to behave in that environment. So it's just using the simulation to train the robot, right? And just lots and lots of iterations. And so a key component of reinforcement learning is you have to do what's called, you have to vectorize the robot. And that means you have to be able to run a script that creates the robot, runs it through a simulation, and then dismantles the robot. And in order to vectorize a robot, you need to control all of your driven joints with these things called articulations within the Omniverse, within the Isaac Sim APIs. And it turns out that spherical joints are not supported with vectorization. So, and so with the Onshape importer, it actually handles that for you by if you have a spherical joint Onshape, when you import, it turns that into 2 revolute joints and a couple of objects that kind of that have the same degrees of freedom as a spherical joint, but it's made up of all revolute joints, and so the articulations will still work in that API, so you can still vectorize your robots. But the problem is when you have joints stacked on top of joints, I was worried about this. It just is, it's a bit of a recipe for round off error in your simulations and just trouble with your joints. However, so are parallel revolute joints, because if they're slightly, just barely not parallel, then they'll bind. And so I was kind of playing with this, and that's what's nice about using spherical joints in the real world, is because they just don't bind. And so if you have complex motions or multiple degrees of freedom going on, then it's really nice to use these spherical bearings in the real world. It really helps with misalignments and that sort of thing. And so yeah, spherical bearings are very common when you really actually build robots, but they're kind of hard to simulate. And so I built the robot with spherical joints. I brought it into Omniverse. I simulated it, and it was a mess. These joints that should be kind of like rigidly attached were moving, were breaking. It was a disaster. And so I said, okay, well, that's not going to work. Let's try parallel revolute joints, and let's just rework it so that this model only uses revolute joints. More accurately, so that it doesn't use any spherical joints. And I went back and did that. And if you look at the new template, you'll see that I've got all these lines for each joint, and those are all constrained to be perfectly parallel. So like all of our suspension members move parallel to each other, and it works. It looks pretty good. So I'm not having problems with those revolute joints binding. And my hunch is that this physics engine can handle almost parallel joints. That's kind of an edge case, right? It handles those pretty well. Whereas multiple revolutes stacked exactly on top of each other, it has a hard time with those. So, it actually, as far as remote control cars go, once I finished with it, I realized this is going to be a lot better template. It's not exactly the same. This is especially with the steering. It's not exactly the same as the F1Tenth steering. It's simplified by quite a bit, but that's actually going to make it work better as a template, because it seems like every remote control car I see has a different steering mechanism. And so with you actually model all of the steering parts, it was going to be a bit of a mess, and you'd have to remodel that kind of part of the template for any remote control car, or for a lot of them. And originally I did that because I was kind of being particular, and I was saying, well, we want to have the exact right steering angles, and we want to have all those masses, the inertias of all those steering components. And then I actually measured a steering component, and it weighed like 2 grams, whereas the car weighs like 5 kilograms. And so it's kind of like, okay, if we use significant figures, the mass of the steering linkages really doesn't matter at all. And so what I've done is I have the servo horn right here. Is that, just kind of, its position doesn't even matter anymore. And then I've got this steering axis that the wheels turn on, and I'm just going to model those as a gear joint. And so basically, if the steering servo moves, I'm going to have the steering move with it. And it's not going to be completely accurate. And if we get into a position where, but honestly, I think it's going to be better. Like, I think what you would do for a more accurate template is, instead of modeling those as a simple gear joint, you might write a little extension that makes a gear joint where you can put in like a plot a curve that says, depending on the servo position, the left wheel is at this position, right? And you could just measure those curves and from the mechanism, and just not model the whole mechanism, but just include those steering angles directly. So there you go. That was one finding, is we're not going to use spherical joints. I've simplified the steering significantly. So here you can see the chassis built off of that. It's just a basic chassis. These are all visual models. They're not at all like the real car. They have some similarity, but we just need some mesh. So I've gone through and weighed all the parts, and we just need a mesh so that we can apply the correct weights. And one thing I found is that, so the whole car weighs like 5.5 kilograms, and the wheels weigh 120 grams each. Then everything else is like less than 30 grams. And when I say less than 30 grams, the parts that are 30 grams are the wheel uprights. And so like the part that attaches to the wheel. So you've got a few heavy parts, especially in kind of the outer, like in that unsprung mass. So like the wheels and uprights, those weights are fairly important. But then the lower A-arm weighs like 10 grams. And I just don't think, I think we can simplify this template process. I would suggest people weigh the whole car, weigh your wheels, your uprights, but I wouldn't worry about the A-arms, and I wouldn't worry about the shocks. They're all really light, and you could just put like estimate 10 grams each for those, or just kind of some small mass.
Yeah, it doesn't need to be exact, right?
No, especially if they're small compared to the overall mass of the car. Because basically you have, those wheels move and can bounce. And so that's an important mass. The chassis is kind of moving around and it's quite heavy, but the shocks themselves, or
how many separate pieces are there altogether?
Altogether, there are quite a few, especially if you include nuts and bolts. But I didn't measure each part individually. We're going from a dynamic simulation standpoint. So I only weighed parts that move relative to each other.
I see.
So it's kind of like, it's more about, instead of having a full weights bill of materials, it's about having a good simulation at the end of this. So then I built the chassis off of that template, and here are the A-arms built off of that same template. So all I do here in Onshape is whenever I need to create some new parts, I create a new part studio, and then I add a derived part. Where is derived part? Right here. And you can go back to that suspension geometry template and bring it in, whatever hard points I need, and then I build off of those hard points and planes. Here's where you get some rougher looking, these are just some basic representative uprights. You'll note, it's interesting, the Traxxas Slash, cars I've done before, the upright actually steers. So you've got the upright that's connected to the suspension with spherical joints, and then that whole thing will turn. But on the Traxxas Slash, there's an upright that attaches to the suspension, and then it has a separate steering axis and another part that actually does the steering. And I hadn't thought of this, but I think you can model any of the car suspensions that way. And if you have a fully steering upright, you just put the end point of this steering axis on the center of the upper A-arms revolute and the bottom one at the other A-arms revolute joint. And you've broken those two, instead of having two spherical joints, you have 3 revolute joints, and it models the same degrees of freedom, and will simulate better in Omniverse. And this will work for either style. So that was kind of a really nice kind of thing that came out of this journey. Is I found a kind of this way of modeling it. It can model the other type of upright, but it only uses revolute joints. It's great. The only thing we don't get here, if a high performance cars will have A-arms that are intentionally not parallel to introduce anti-dive and anti-squat dynamic performance characteristics, and we're not going to be able to model that with this. I don't know how. I wouldn't know how yet. Maybe we can come up with a way, but remote control cars don't typically have that. They don't typically get that sophisticated. Here's a little steering horn. Here are some basic shocks, some basic wheels, and then here's the assembled car. With
a lot of progress, man. You did this all like since the last live stream?
Yeah.
Wow.
I mean,
Impressive.
not all of it, but I redid. I had the arms already, but I had to redo the template, all the steering, and I had to redo a lot of the template to fix the joints. And yeah. So there we go. Here's the template. It's revolute joints, and then these shocks are prismatic linear joints, naturally, but not a single spherical joint in this template. And and before we move on, let me just review questions, and I'm happy to answer any questions about this CAD work. It's definitely not realistic, right? This is kind of as far as CAD goes, I would call this a simulation schematic, right? It just gives you an idea of what the parts are. They have meshes we can apply weights to, relatively similar centers of gravity of the real parts, but definitely representative of the parts rather than accurate, right? So I don't see any questions about the CAD, and so let's step into Omniverse. And this CAD is done, and so we're going to be in Omniverse until we can drive this thing with our Xbox controller, and it looks like it's kind of convincing, like it's a real car driving, like a real control car driving around. So I'm going to close. Well, I'm going to close this, and I'm going to open Isaac Sim. Let's see. Launching Isaac Sim on my other screen. I'll bring it on once it's launched.
That's not a bad screen to look at while we're waiting.
Thanks.
Love that picture.
I love,
Crazy.
Two of my favorites are just any photo of this spatial launching off, and that first flight photo with the Wright brothers. I just love those photos.
You're the right person for this live stream.
Oh, did someone say that? That's kind.
No, that's me.
Oh, that's you. Okay, well, thank you. That's kind. It's launching, almost there. There we go. So I've imported into the is it going? Oh, I'm not on VPN, folks. Just a minute. Yeah, suffice to say, I do not have any concerns about the security of NVIDIA systems. I've got a
Oh, we got him frozen. Eric will be back in 1 minute. That's one of the benefits of StreamYard. Cloud-based. There he is. He's back.
Yeah,
You froze up. You froze up for a minute.
Oh, because I connected to VPN.
Yeah.
All right. It looks like we haven't done the import yet. So let's just go through this. How I want to do this. I'm going to delete you. We're going to start from scratch here because there's really not much done here. Let's see here. Here, just a second. All right. So we've got a new scene here. File, import from Onshape. Here's the template. Let's import this CAD. Great. There it is. Now what I want to do is I'm going to go ahead and save this. Well, actually, let's go ahead and create a ground plane. And if we run it, it's got some problems, right? But we see that a couple of our joints are in there. We'll walk through this here after I just save a few things. So first we'll save the scene. I'm going to call this environment. Where is it? Environment. There we go. Well, it froze because I was authenticating and VPNing and doing all the secure stuff. That's why I froze. So, all right. So I've created this environment. Now what I want to do is I want to create a new sublayer. I've created. What happened there? Create a sublayer. Oh shoot. F1Tenth.
Data Juggler's asking about Jen. Jen is on vacation right now. Sure, she'll fill us in on all the details as soon as she gets back, but she'll be back soon.
Just a second. I'm getting an error here. I'm not sure what's going on here. Got that saved. I'm going to relaunch Isaac Sim real quick.
Is it hard not having Jen here to have her engineering kind of input as you're working through these things?
Oh, look, there's my other favorite photo.
I know, I see it. Beautiful.
Yeah. She's great. Right? So she's great because she asks, doesn't have an engineering design background. And so she asks great questions. But she has a very analytical mind. So she asks really great questions. And then of course, whenever we're doing any kind of Python work, she's invaluable, right?
Yeah.
She's just a wealth of knowledge when it comes to Python. So Yeah, definitely miss having Jen.
We all miss her. She'll be back soon. I'm sure she'll be back some nice coffee from wherever she's traveling to.
Yeah.
A nice little trivia from Zia here.
Oh, cool.
The biplane wings helped save the Wright brothers from dangerous stalls.
Did you know that they didn't have any kind of flaps yet, and so they actually twisted the wings to steer the plane?
Brave people.
Another interesting one is the plane was aerodynamically unstable. So if you just didn't do anything, it would totally crash. And they were really hard to fly for the first few years until they figured out that if you put the center of mass, and arrange that with the center of pressure of the wings, and it would become stable, and you'd have stable flight. Let's see. Let's file. Let's try this again. What I'm trying to do is I'm trying to create a sublayer and move all of the car stuff to the sublayer. And what that'll let me do is, if I have got the environment in the parent layer, and then I've got all of the car stuff in a child layer, we'll be able to put this car into different environments to drive it around.
Nice.
Which is definitely, I think, definitely what we want. And then we can just rig it in this flat plane environment. And then I've got some other NVIDIAns working with me. One of them is making some tracks. We'll be able to just put it into tracks.
Very cool.
Let's see, but it wasn't letting me create a sublayer for some reason. So let's try again. It's airing. Let me just try a different name or something.
Was there an error that popped up? No.
In the console, there was.
There was.
There we go. You know what? Maybe it didn't like that it had the same name as its containing folder, F1Tenth.
Interesting.
I'm not sure, but I just put car.usd in, and that works for me. Let's set that as the authoring layer. What we can do now is we can take the car and drag it in there. And so now what this is saying is the delta on the world prim, and it's going to add the car and everything it contains to the world prim. So, and let's save that. So now our environment's in this parent layer and in the full car, in the cars in the child layer. So let's start to fix some of these issues we saw. Let's run it again. Okay, so we get all these errors. These are common errors when we're working with articulations. So that import not only brought in the geometry, it made all these joints for us. So all the joints that we had in the CAD system, it made those for us. So that's nice. Oh dear. I just remembered. I misnamed these joints. Okay, let's see here. So this is where's the front? This is the front on this side. So those ones are correct. This is the rear left. This is the rear right. Okay, let's rename those. Oh, I can't. There's a problem with renaming joints that I was having trouble with. So we'll just leave it for now and remember that those are named wrong. It's not the end of the world. Okay. Let's look at our console. Let's clear it. Only do warnings, and then run the simulation, and then stop it. Let's read what these warnings are saying. Okay. It talks about these joints being part of an articulation. But it's saying it's not supported, right? That's actually not the problem. Let's go up higher. Here we go. This appears to be a part of a closed articulation, which is not supported. Please exclude one of the joints. And it's got all these errors about that on these joints. So when it comes to simulating joints, there are generally two different solvers. You've got your video game solver, which can have a lot of joints, but it's not the most accurate. So joints can move a little bit, they can be out of position. And then, so if you're doing engineering simulations, you typically want to use what's called a reduced coordinate solver or an articulation solver. And that's what we've got here. So if you look at the full car, the Onshape importer is smart enough. It knows that we're doing robots. And so it sets an articulation root right here. It adds an articulation root to that parent prim. And what it says is that all of these children are part of an articulation. Now, I think what we're going to want to do is move that articulation root from here to the chassis, because we want the chassis to explicitly be like the center of our articulation as far as any loops and things go. So articulation, so we just add an articulation root right there.
Oh yeah, good tip from Zia. Don't forget to save.
Yeah. Did I say
Oh, Yitsu, that was here. Very cool from Digital Bot Lab. What's up, Yitsu?
Let's see. Where's that articulation root? Physics, rigid body, collide. Here it is. Articulation root. We should, if you run it again, we should get the same effect with lots of problems. Okay. It made it even worse, but sometimes things get worse. I think the next thing we're going to do, and there, let's save, as Zia suggested. We can just save the car layer, which is really all I've been changing so far. Yeah. The next thing I want to do is add a collision group. There you go. A collision group just lets us make groups of colliders and say which ones can and don't collide with each other. In this case, when you say filtered groups, it says, I don't want any prims in this group to collide with any of the filtered groups. And so if we select itself, that's saying, I don't want any of the prims in this group to collide with each other. So then we add any colliders to this group we want. I can filter by colliders now. And I just want to select everything in the car. So select you. Can I shift select? I believe that worked. Yeah, so we want to select all of the car parts, but not the collision ground plane. And that will, oh, I didn't want to snap that. Okay, and select. So now these objects will not collide with each other. Okay, they just passed. That's a little more stable. But we're still getting these errors. And what I was getting at is, if you have an articulation and you're using the articulation solver, you can't have any loops. They have to be kind of just end-to-end connected. And the way you can get around that is you have to pick some joint and specify that joint is not part of the articulation, and that breaks up the loop. So let's just do that. And if you look, these upper A-arm joints, the solver just kind of runs to those last, or to some joint last. Here, these ones you can see, they just fell to the ground. That onboard joint just is ignored. And there's some joints on these shocks that's happening too. That's what's going on there. So let's fix it. All we do is pick the joints that we wanted to ignore. I like these upper A-arm joints for the principle of no good reason. And you just select exclude from articulation. And we'll do this with this rear upper left. Exclude from articulation. Let's do that with the... by the way, if you notice, I've named these as the two things that are connected, separated by two underscores. So if there's single underscores, those are spaces. If there's double underscores, that represents more of like a, I don't know, like a hyphen. But the chassis to the arm, to the rear upper left arm, that's what that means. So we want the chassis to the front. Here we go. Chassis to the front upper arms, those two. So let's exclude those from the articulation. And let's exclude the front upper left arm from the articulation. Now if we run it, it's doing a lot better. These shocks are still messed up because they have their own loop. So we're going to have to get rid of that loop. But notice that the arms are all behaving like they should. So let's see here. We want to go to the chassis to the shock. Chassis to the shock, front upper right. Chassis to the shock, front upper left. Those are our front shocks. Let's exclude those upper joints from the articulation. And we want the chassis to the shock. There should be two more of those. Those are the actual shock joints. Arm shock, arm shock. I'm not seeing it, but it's got to be in there. There's that one. There's that one. No, not that one. Arm. Oh, I misnamed these two. Oof, looks like I got some naming convention to fix, huh? Exclude. That's one of the hardest things for me is going back and naming things well when I'm trying to move fast. Great. So let's run it now. And you can see that nothing is, they're looking good. There's a good chance that these are spinning in place. Oh, no, they're not. Those are revolutes now, not sphericals. But that guy is just spinning, right? Oh.
It's funny. It's slowing down.
Yeah. Let's go to that chassis servo horn joint. And let's see if it works for us this time. A little bit of joint friction. There we go. Well, almost. Let's add a little bit more. There we go. That's a little better. See how it's not spinning forever? But really what we should do to that is let's see, where are we in it? Let's go ahead and add a driver to it. So if we go, we're in that chassis, the servo horn joint, we can add a physics angular drive. And here it is. And we want the target position to be 0. It's still not going to do anything. See how it just behaves the same still? I'll zoom right in on it. And that's because, man, I always forget. But if you have the angular, it does move. Oh, look at that. It's tracking those positions and velocities for us. That's kind of cool right here. You've got to set the damping and the stiffness. And if it's an angular drive, I believe it's high damping and low stiffness. There you go. Nope. There we go. So now I can say what angle. There's at 10 degrees now. See how responsive it is. No, I can't just drag and have it move real time, but so that's that straight down. Yeah, so now I can move this thing, right? That's kind of cool. So now we've got our steering servo is kind of, it has an angular driver. So that means we're going to be able to use a script or use code and find this angular drive and move that servo. And the same thing, if we pick all 4 wheels, those should be knuckle wheel. Here's 1, 2 of those. Oh, I call those upright. Yes, that's right. In the rear, they're uprights to the wheels. In the front, it's knuckles to wheels. Let's add an angular drive to those. For those, let's do a target velocity. 10, we're just making up a number. And then we'll do a high damping and low stiffness. Oh, it just creeped a little bit. Let's make that target velocity higher. There we go.
Nice.
Yeah, let's make it 500. Make it move. You got too high. It's actually not. How's the bumpiness?
Off into the sunset.
Yes, there we go. We needed an environment with a sunset. Cool. So
Great, man.
we look at this. One thing is, you notice it's dragging on the ground. So, because there are no springs yet. And the other thing is, let's make it steer a little. Let's make it steer. Right now, in theory, what we want to do is grab this servo. And if we make it to like 10 degrees, let's make it like 30 degrees even. That it should be turning, right? For that, and I've never done this before. I hope it goes smoothly. It probably won't. Let's create a gear ratio here. So we're going to create a physics joint. Oh, you got to select the stuff first. We want a gear joint. So let's choose the upright knuckle right. That's my my revolute joint on that tire, on that wheel. And let's choose the servo horn. And now I think we can go to create physics gear joint. No, I can't. All right. Create physics joint. I can't create any joints. Why can't I create any joints? I don't know how to create a gear joint. Let's just try this. Let's just create 2 prims. Select 2 prims. Create physics joint gear joint. Let's look at its properties now. Oh, you just need you need 2 bodies, huh? Let's think about this. Hinge 0, hinge 1, add target. See, that makes sense to me, right? That I have to select 2 joints for the hinges, right? But having the 2 bodies, that does not make sense to me. Let's try this. Let's delete that. Let's just create 1 prim. Create physics. I can do with that. So I think what I'm going to do, let's just create one. Create physics joint. Well, let me do that. Let's make it here in the car, I guess. You know what it probably has to do is determining the articulation. So let's just choose like the front right wheel, I guess. And create a physics joint. So now we're just kind of logically saying this is attached to that front right wheel. I don't know if this is going to work.
Fingers crossed.
Here's the servo horn. And we want the upright knuckle. Right. Sure, why not? Key ratio is 1. Okay. We had an error, but it looked like it's a pretty good little error message. Articulation cannot contain a gear joint. Please exclude it from articulation. Okay, that's 1. Neither parent nor child of hinge 0 refer to body 0. Okay, and so I think for the bodies have to be kind of related to those spherical joints, it looks like. So first, let's take care of this one. Exclude this from this gear joint from the articulation. And second, let's edit it. The wheel was, the wheel was not part of that either. So let's, for body 0, let's add the servo horn. Is that right? Yeah. If I can find it. There it is. Select. And for body 1, let's do the knuckle. Steering knuckle left. I want steering knuckle right. Let's see if that works. Look at that. Is it turning? I think I saw it turn, but let's really crank it up, that angle. Make it like 30. What is it right now? Oh, it is 30 degrees. Make it 90 degrees.
And go in a circle.
No, it's just going to turn it really hard, but it didn't seem to turn it. Let's try it again. No errors. Well, looks like I've got some research to do on gear joints, but that's what. If we can't get it to work that way, then we'll just write a script or something. Or what I could do is just put a driver on both wheels. I think I'll do that. I'm going to, because this doesn't work with articulation anyway. And what we can do here is go to the upright knuckle right. And the upright knuckle left. And add it as physics angle drive. Make a target position of like 15 degrees, and we'll say 100. There you go. Yeah, that's going to be fine. We'll just do that. We'll just control both wheels and kind of have them be the same. Kind of have them be the same angle. Now just ditch that. I guess we could have the just for visualization if we want. We can make that servo horn match, right? Yeah, I think that's better. Oop. So now it's steering. See, 3 minutes left. So I'm going to go ahead and wrap up. Oh, well, great question from Zia. How is steering done on some of the sample bots? I think most of them are differential robots. So they don't have like a steering linkage. They just more like a one wheel will go, only one wheel will go, or the wheels will go opposite directions. So that's a little bit different style of steering. So all we've got to do now is add spring force and damping to these shocks. I'll just show you real quick kind of where that is. If you go to the shock joints, like right here, go to advanced. Excuse me, here in the prismatic joint. First, you set upper and lower limits. And then if the shock ever exceeds those limits, it'll apply whatever stiffness and damping you've set. So, and these properties. So that's how. We'll take these prismatic joints for these shocks, and we'll add springs and dampers to those. And at that point, we should have a drivable car.
Exciting.
And I already have an extension that I can use to control stuff with a gamepad, and I'll just reconnect that to this prim structure, and we should be able to drive this around.
Fun. You got a lot done today.
Yeah.
A lot of errors removed.
Yeah. So hope you all enjoyed. It was more of a just watch me go session than usual, but I hope you enjoyed it. And hopefully next week I can show off a car that we can drive around with a gamepad.
Awesome. And continue the chat if you want on the Jet Racer channel on the Omniverse Discord server, where Eric and others in the community are hanging out. Really great work, though.
Thank you.
It's fun to see it come together.
All right. In that case, I think we will wrap up 1 minute early. We'll see you all next week.
Bye.